My name is Darcy and I'll be talking about stable model semantics and answer set programming. So why is stable model semantics necessary? Classical propositional logic is monotonic, meaning adding facts never invalidates conclusions. If we have the premises P and P implies Q, the conclusion is Q, and if we add the premise R, conclusion Q still holds. In answer set programming, it requires a non-monotonic logic system. If new information arrives, conclusions may be withdrawn. If we have this program P if not Q, it has one stable model P, since no rules invalidate P being true. If we add the fact Q, now the rules body not Q fails, so P is no longer a stable model. What is a stable model? So a stable model, also called an answer set, is a minimal model of a program's reduct. It captures the intended meaning of a logic program. Stable models must be self-supported, meaning every true item is supported by a rule whose body is satisfied in the model. An example in ASP is this program, which has a stable model of P and Q. P is a fact, so it is supported. Since P is true, Q is true via this rule. So, reducts. Given a program pi and a candidate set of atoms I, which is the candidate interpretation, the reduct pi I is produced from pi as follows. For every atom in interpretation, remove any rule from pi containing not A. Remove all remaining negative literals from pi. So formally, here's the definition of pi I, where body plus is the positive literals in the body of the rule, and body negative is the negative literals. Note that this means the reduct pi I contains only positive literals, and we'll get to why that's important. The interpretation is a stable model of pi if the interpretation is a minimal model of the reduct pi I. The intuition is that if we assume the interpretation is true, and we simplify the program to pi I under that assumption. A minimal model is a model M of a program pi such that there is no proper subset M prime, which is also a model of pi. In other words, if any atom is removed from a minimal model, it is no longer valid. If a program contains no negative literals, it is called a positive program. For a positive program, a stable model is necessarily the minimal model. An example of this is the reduct is, since it must be a positive program, the minimal model is the stable model of pi. So how is this used in ASP? ASP solvers like Klingo rely on stable model semantics to find solutions to logic programs. Solutions in ASP are the stable models of the program, hence the name answer set programming. So first it guesses an interpretation I of atoms assumed to be true, then it checks whether the interpretation is a stable model using the reduct. The check process is to construct the reduct of pi in relation to I, find the minimal model M of the reduct, and then if M equals the initial interpretation, then the interpretation is a stable model of pi. Otherwise, we try again. The differences to classical logic is a stable model M must also be a model in classical logic. However, a classical model M is not necessarily a model within stable model semantics. So classical logic uses strong negation, where not A means A is provably false in all models. So A is a contradiction. Stable model semantics treat not A as a failure to prove A. It is not ruled out entirely. Classical logic is also monotonic, as we've discussed in the previous slide. Adding facts never invalidates conclusions, whereas stable model semantics is non-monotonic. So in stable model semantics, we can have multiple stable models. So a program can have 0, 1, or multiple. If it has no stable models, the program pi is unsatisfiable or inconsistent. An example of in ASP is the fact P and the constraint not P, or P implies false. If it has one stable model, it is the deterministic solution. Here's an example in ASP. And if it has multiple stable models, each stable model is a valid solution to the initial problem, or the initial program. Here's an example of in ASP where either one or the other of P and Q can be true, but not both, and not neither. Klingo iterates all stable models if you ask it to, and can count how many models exist. So now, two logic programs pi1 and pi2 are equivalent if they have exactly the same set of stable models. So every stable model of pi1 is a stable model of pi2 and vice versa. Here's an example in ASP with two programs. Pi2 is equivalent to pi is the same as pi1, but it has one extra constraint or one extra rule, and both have the exactly one stable model, which is just p, so they are equivalent. Two programs pi1 and pi2 are strongly equivalent if for every logic program pi prime, pi1, the combination of pi1 and pi prime and pi2 and pi prime have the same stable models, where the combination is the union of those two programs, i.e. the programs remain equivalent under any extension pi prime, where an extension is another program that we combine. In classical logic, equivalence is the same as strong equivalence, or equivalence if and only if strong equivalence, since the system is monotonic. In stable model semantics, since it is a non-monotonic system, strong equivalence implies equivalence, but not the other way around. An example in ASP is the program that we had on the previous slide. This is equivalent. These two programs are equivalent, but not strongly equivalent, since adding the fact q removes any stable model of pi2 containing p. Here's a practical example in Klingo of a graph coloring problem. So we define some vertexes and some edges between those vertexes. So this is a not a fully connected graph. And then we define when red is valid. So it has to be a vertex, and it has to be not blue and not green because they're all mutually exclusive. And then we do the same thing for every other color. And then we add the constraints such that for any two vertices u and v, if they have an edge, then both the vertices can't be red, and then can't be green, and so on for every color. Of course, we can do this using variables, but here we're just showing the manual grounding of the three colors. And if we run this and try and look for all outputs with the 0 and ask it to show every color, then here is the stable models, the 6 stable models of this program, which is any interpretation such that the rules hold. And that is it. Thank you for listening. Goodbye.